Lightning protection is required for structures with a height greater than 20 feet, a roof area greater than 8,000 square feet, or antennas mounted on a mast or tower. Since the antenna and mast are combined to be over 15 feet tall and mounted on the tallest point of a 40-foot high building, lightning protection is required. You can bond the lightning protection system to the existing ground rods at the electrical panels. However, these ground rods may not provide adequate protection for the antenna and amplifier. The National Electrical Code requires that separate ground rods be used for lightning protection systems. The best option for lightning protection is to install a dedicated system that includes air terminals, which are lightning rods mounted on the highest point of the building and the antenna. It also includes down conductors, which are lightning wires connecting the air terminals to the ground rods. It also includes ground rods driven into the earth to a depth of at least 10 feet. Firstly, hire a qualified lightning protection contractor. Secondly, design a system that meets the requirements of National Fire Protection Association 780 and local building codes. Thirdly, install the system according to the manufacturer's instructions. Fourthly, test the system to ensure proper operation. Surge protection devices should also be installed to protect the equipment from electrical surges caused by lightning. Regular inspections and maintenance of the lightning protection system are crucial to ensure its effectiveness. When determining lightning protection requirements, several factors need consideration to ensure adequate safety for structures and personnel. These factors encompass building height, roof area, occupancy type, geographical location, and the presence of sensitive electronic equipment. Firstly, building height is a critical determinant. Structures exceeding a certain height, typically around 50 feet, are at a higher risk of lightning strikes due to their increased exposure. Taller buildings intercept more lightning strikes than shorter ones, necessitating robust lightning protection systems. Secondly, the roof area significantly influences lightning protection needs. Larger roof areas provide a greater surface for lightning to strike, increasing the likelihood of damage. Buildings with expansive roofs, such as warehouses or industrial facilities, require comprehensive lightning protection measures to distribute the electrical current safely. Thirdly, occupancy type plays a vital role in determining the level of lightning protection required. Buildings housing critical infrastructure, such as hospitals, data centers, or emergency response facilities, demand enhanced protection due to the potential for severe disruption and loss of life. Similarly, structures with a high concentration of occupants, like schools or office buildings, necessitate stringent lightning protection measures to safeguard human safety. Fourthly, geographical location significantly impacts lightning strike frequency and intensity. Regions with high thunderstorm activity, such as the southeastern United States or tropical areas, experience a greater risk of lightning strikes. Buildings in these areas require more robust lightning protection systems to withstand the increased threat. Fifthly, the presence of sensitive electronic equipment necessitates specialized lightning protection measures. Electronic devices are highly vulnerable to damage from lightning-induced surges, which can disrupt operations and cause costly repairs. Buildings housing sensitive electronics, such as computer servers, medical equipment, or telecommunications systems, require surge protection devices and grounding systems to mitigate the risk of damage. To install a lightning protection system, 1. Conduct a thorough risk assessment. This involves evaluating the factors mentioned above to determine the level of protection required. The assessment should consider the building's height, roof area, occupancy type, geographical location, and the presence of sensitive equipment. 2. Select appropriate lightning protection components. Based on the risk assessment, choose the necessary components, including air terminals, down conductors, grounding electrodes, and surge protection devices. Ensure that the components meet industry standards and are suitable for the specific application. 3. Install air terminals at strategic locations. Air terminals, also known as lightning rods, are installed on the highest points of the building to intercept lightning strikes. Position them at regular intervals along the roof and on any prominent features, such as chimneys or antennas. 4. Connect down conductors to air terminals. Down conductors are heavy gauge wires that provide a low impedance path for lightning current to flow to the ground. Connect them to the air terminals and route them along the building's exterior to the grounding electrodes. 5. Install grounding electrodes to dissipate lightning energy. Grounding electrodes are buried in the earth to provide a safe path for lightning current to dissipate. Install them at multiple locations around the building and connect them to the down conductors. 6. Implement surge protection measures to protect electronic equipment. Install surge protection devices at the electrical service entrance and at individual equipment locations. These devices divert excess voltage from lightning strikes, preventing damage to sensitive electronics. 7. Inspect and maintain the lightning protection system regularly. Conduct periodic inspections to ensure that all components are in good condition and functioning properly. Repair any damage or corrosion promptly to maintain the system's effectiveness. Remember that hiring a qualified lightning protection contractor is essential for ensuring a safe and effective installation. These professionals have the expertise and experience to design and install systems that meet industry standards and local building codes. When selecting lightning protection components, several factors should be considered to ensure optimal performance and reliability. These factors include material selection, corrosion resistance, mechanical strength, and compliance with industry standards. Firstly, material selection is crucial for lightning protection components. Copper and aluminum are the most commonly used materials due to their excellent conductivity and corrosion resistance. Copper is generally preferred for air terminals and down conductors, while aluminum is often used for grounding electrodes. Secondly, corrosion resistance is essential for ensuring the long-term durability of lightning protection component. Components exposed to the elements must be able to withstand corrosion from moisture, chemicals, and other environmental factors. Copper and aluminum offer good corrosion resistance, but additional coatings or treatments may be necessary in harsh environments. Thirdly, mechanical strength is important for withstanding the forces exerted by lightning strikes and wind loads. Air terminals and down conductors must be able to withstand the impact of lightning strikes and the stress of high winds. Choose components with adequate mechanical strength to prevent damage or failure. Fourthly, compliance with industry standards is crucial for ensuring the safety and effectiveness of lightning protection systems. Lightning protection components should meet the requirements of standards such as National Fire Protection Association 780 and Underwriters Laboratories 96. These standards specify the design, installation, and testing requirements for lightning protection systems and components. To ensure the effectiveness of a lightning protection system, regular inspections and maintenance are essential. These activities help identify and address any issues that could compromise the system's performance, such as corrosion, damage, or loose connections. Firstly, conduct visual inspections of all lightning protection components. Check for signs of corrosion, damage, or loose connections. Pay particular attention to air terminals, down conductors, and grounding electrodes. Secondly, test the grounding system to ensure its effectiveness. Use a ground resistance tester to measure the resistance of the grounding electrodes. The resistance should be below a specified threshold, typically 25 ohms, to ensure adequate grounding. Thirdly, repair any damage or corrosion promptly. Replace any damaged or corroded components to maintain the system's integrity. Clean and treat corroded surfaces to prevent further degradation. Fourthly, tighten any loose connections. Ensure that all connections between components are tight and secure. Loose connections can increase resistance and reduce the system's effectiveness. Fifthly, keep the area around the grounding electrodes clear of obstructions. Vegetation, debris, or other obstructions can interfere with the grounding system's performance. Keep the area clear to ensure proper grounding. Sixthly, document all inspections and maintenance activities. Maintain a record of all inspections, tests, and repairs. This documentation can be helpful for tracking the system's performance and identifying any recurring issues. Remember that regular inspections and maintenance are crucial for ensuring the long-term effectiveness of a lightning protection system. By identifying and addressing any issues promptly, you can help protect your building and its occupants from the hazards of lightning strikes. Here's more about grounding electrodes. Grounding electrodes play a critical role in lightning protection systems by providing a low impedance path for lightning current to dissipate into the earth. The selection, installation, and maintenance of grounding electrodes are essential for ensuring the effectiveness of the lightning protection system. Firstly, choose appropriate grounding electrode materials. Copper and aluminum are the most commonly used materials for grounding electrodes due to their excellent conductivity and corrosion resistance. Copper is generally preferred for its superior conductivity, but aluminum can be a cost-effective alternative in some applications. Secondly, select the correct type of grounding electrode. Several types of grounding electrodes are available, including ground rods, ground plates, and concrete-encased electrodes. Ground rods are the most common type and are typically driven into the earth to a depth of at least 8 feet. Ground plates are buried horizontally in the earth and are often used in areas with shallow soil. Concrete-encased electrodes are embedded in concrete foundations or footings and provide excellent grounding performance. Thirdly, install grounding electrodes at multiple locations. Multiple grounding electrodes should be installed around the perimeter of the building to provide a distributed grounding system. The electrodes should be spaced at regular intervals and connected to the down conductors. Fourthly, ensure proper grounding electrode depth. Grounding electrodes should be installed to a depth where they are in contact with moist soil. This helps to reduce the resistance of the grounding system and improve its effectiveness. Fifthly, bond all grounding electrodes together. All grounding electrodes should be bonded together with a grounding conductor to create a common grounding system. This helps to equalize the potential between the electrodes and prevent voltage differences that could damage equipment. Sixthly, test the grounding system regularly. The grounding system should be tested periodically to ensure that it is functioning properly. Use a ground resistance tester to measure the resistance of the grounding electrodes. The resistance should be below a specified threshold, typically 25 ohms, to ensure adequate grounding. Seventhly, maintain the grounding system. The grounding system should be inspected regularly for signs of corrosion, damage, or loose connections. Any issues should be addressed promptly to maintain the system's effectiveness. More information is also helpful on surge protection. Surge protection devices play a crucial role in lightning protection systems by protecting sensitive electronic equipment from damage caused by lightning-induced surges. These devices divert excess voltage from lightning strikes, preventing it from reaching the equipment and causing damage. Firstly, install surge protection devices at the electrical service entrance. Surge protection devices should be installed at the electrical service entrance to protect the entire building from lightning-induced surges. These devices divert excess voltage from lightning strikes before it can enter the building's electrical system. Secondly, install surge protection devices at individual equipment locations. Surge protection devices should also be installed at individual equipment locations to provide additional protection for sensitive electronics. These devices protect equipment from surges that may have bypassed the service entrance surge protection devices. Thirdly, choose surge protection devices with appropriate voltage and current ratings. Surge protection devices should be selected with voltage and current ratings that are appropriate for the equipment they are protecting. The voltage ratings should be higher than the normal operating voltage of the equipment, and the current rating should be sufficient to handle the expected surge current. Fourthly, select surge protection devices with low clamping voltage. The clamping voltage is the voltage at which the surge protection device begins to divert excess voltage. Choose devices with low clamping voltage to provide better protection for sensitive equipment. Fifthly, install surge protection devices in accordance with manufacturer's instructions. Surge protection devices should be installed in accordance with the manufacturer's instructions to ensure proper operation. Follow the instructions carefully and use appropriate wiring and grounding techniques. Sixthly, test surge protection devices regularly. Surge protection devices should be tested periodically to ensure that they are functioning properly. Use a surge protection tester to verify that the devices are diverting excess voltage as intended. Seventhly, replace surge protection devices after a lightning strike. Surge protection devices may be damaged after a lightning strike, even if they appear to be functioning properly. Replace surge protection devices after a lightning strike to ensure continued protection for sensitive equipment. Let's look at some specific requirements in National Fire Protection Association 780. National Fire Protection Association 780 standard for the installation of lightning protection systems provides comprehensive requirements for designing, installing, and maintaining lightning protection systems. The standard covers various aspects of lightning protection, including air terminals, down conductors, grounding electrodes, and surge protection devices. Firstly, National Fire Protection Association 780 specifies requirements for air terminal placement. Air terminals, also known as lightning rods, should be placed on the highest points of the building and at regular intervals along the roof. The standard provides guidelines for determining the spacing and location of air terminals based on the building's height, shape, and occupancy. Secondly, National Fire Protection Association 780 sets requirements for down conductor routing. Down conductors are heavy gauge wires that provide a low impedance path for lightning current to flow to the ground. The standard specifies requirements for the size, material, and routing of down conductors to ensure that they can safely carry lightning current to the grounding system. Thirdly, National Fire Protection Association 780 outlines requirements for grounding electrode installation. Grounding electrodes are buried in the earth to provide a safe path for lightning current to dissipate. The standard specifies requirements for the type, size, and location of grounding electrodes to ensure adequate grounding performance. Fourthly, National Fire Protection Association 780 addresses requirements for surge protection device selection and installation. Surge protection devices protect sensitive electronic equipment from damage caused by lightning-induced surges. The standard provides guidance on selecting and installing surge protection devices to protect equipment from voltage spikes and transient current. Fifthly, National Fire Protection Association 780 provides requirements for system inspection and maintenance. Lightning protection systems should be inspected and maintained regularly to ensure that they are functioning properly. The standard specifies requirements for visual inspections, testing, and maintenance to identify and address any issues that could compromise the system's performance. Sixthly, National Fire Protection Association 780 includes requirements for lightning protection system documentation. Lightning protection systems should be documented to provide a record of the system's design, installation, and maintenance. The standard specifies requirements for documentation including drawings, specifications, and test reports. Seventhly, National Fire Protection Association 780 addresses requirements for lightning protection system modifications. Any modifications to a lightning protection system should be made in accordance with the standard. The standard specifies requirements for modifying existing systems to ensure that the modifications do not compromise the system's performance, and more specifically on electrical surges. Electrical surges are transient voltage spikes that can damage or destroy sensitive electronic equipment. These surges can be caused by lightning strikes, power outages, or other electrical disturbances. Surge protection is essential for protecting equipment from the damaging effects of electrical surges. Firstly, understand the causes of electrical surges. Electrical surges can be caused by various factors including lightning strikes, power outages, switching operations, and equipment malfunctions. Understanding the causes of surges can help you take steps to prevent them. Secondly, identify the types of equipment that are vulnerable to surges. Sensitive electronic equipment such as computers, televisions, and appliances are particularly vulnerable to damage from electrical surges. Identify the equipment that needs protection and take steps to protect it. Thirdly, install surge protection devices at the electrical service entrance. Surge protection devices should be installed at the electrical service entrance to protect the entire building from electrical surges. These devices divert excess voltage from surges before it can enter the building's electrical system. Fourthly, install surge protection devices at individual equipment locations. Surge protection devices should also be installed at individual equipment locations to provide additional protection for sensitive electronics. These devices protect equipment from surges that may have bypassed the service entrance. Surge protection devices. Fifthly, choose surge protection devices with appropriate voltage and current ratings. Surge protection devices should be selected with voltage and current ratings that are appropriate for the equipment they are protecting. The voltage rating should be higher than the normal operating voltage of the equipment, and the current rating should be sufficient to handle the expected surge current. Sixthly, select surge protection devices with low clamping voltage. The clamping voltage is the voltage at which the surge protection device begins to divert excess voltage. Choose devices with low clamping voltage to provide better protection for sensitive equipment. Seventhly, install surge protection devices in accordance with manufacturer's instructions. Surge protection devices should be installed in accordance with the manufacturer's instructions to ensure proper operation. Follow the instructions carefully and use appropriate wiring and grounding techniques. Add-on electrical grounding. Electrical grounding is the process of connecting electrical equipment and systems to the earth to provide a safe path for fault current to flow. Grounding is essential for protecting people and equipment from electrical shock and damage. Firstly, understand the purpose of electrical grounding. Electrical grounding provides a low impedance path for fault current to flow to the ground. This helps to trip circuit breakers or fuses, which de-energizes the circuit and prevents electrical shock. Secondly, identify the types of grounding systems. Several types of grounding systems are available, including grounded, ungrounded, and impedance-grounded systems. The type of grounding system used depends on the application and the requirements of the electrical code. Thirdly, install grounding electrodes to provide a connection to the earth. Grounding electrodes are buried in the earth to provide a connection to the earth. The electrode should be installed in accordance with the electrical code and should be of sufficient size and number to provide adequate grounding. Fourthly, bond all metal parts of the electrical system together. All metal parts of the electrical system, including equipment enclosures, conduit, and grounding conductors, should be bonded together to create a common grounding system. This helps to equalize the potential between the metal parts and prevent voltage differences that could cause electrical shock. Fifthly, test the grounding system regularly. The grounding system should be tested periodically to ensure that it is functioning properly. Use a ground resistance tester to measure the resistance of the grounding electrodes. The resistance should be below a specified threshold to ensure adequate grounding. Sixthly, maintain the grounding system. The grounding system should be inspected regularly for signs of corrosion, damage, or loose connections. Any issue should be addressed promptly to maintain the system's effectiveness.